Okay, we can do that.
But how shall I? Okay, now I see the issue. How shall I make? Oh, okay.
You're good? Yeah.
Okay, that's good.
That's a better idea.
There. So, good afternoon, everyone.
Do you want to use the?
Hi, good afternoon, everyone. And welcome to the plenary talk for the afternoon on Wednesday. So I'm Raymond Spiteri. I'm a professor in the Department of Computer Science at the University of Saskatchewan, and it is my great pleasure to introduce to you Jingwei Wu. Jingwei is an associate professor in the Department of Applied Mathematics at the University of Washington. She's been there since 2021, and she's also an adjunct associate professor at the Boeing Department of Aeronautics and Astronautics since this year. She received her BS in computational math from Peking University of China in 2006, and her PhD in applied math from the University of Wisconsin-Madison in 2011. She received an NSF Career Award in 2017 and a Teaching for Tomorrow Award from Purdue University when she was an assistant professor there in 2015. Jingwei's research is on development and analysis of efficient structure preserving methods for kinetic equations and related problems in multiscale modeling and simulation. Her talk today is on high order asymptotic preserving and positivity preserving time discretization for multiscale hyperbolic and kinetic equations. And you know, as a numerical analyst, these are very important properties that, you know, especially the applications people want from their numerical solutions. So not having them is not necessarily a good thing. Having them is a great thing. And we look forward to Jingwei's talk.
Thank you very much, Ray, for the very kind introduction. Also, I would like to thank the organizers for giving me this opportunity, for inviting me, and it's a real honor to having this opportunity to present here. It has been a great conference so far, and I enjoyed it very much. So I'm going to share with you some recent work I did with my collaborators, Gottlieb, Zhang, Ruwen Shu, and Xiangxun Zhang on the development of structure preserving time discretization methods. So I should say that when we so in the search of the methods, we are really driven by the application to hyperbolic and kinetic equations, which is the field I come from. So, and in particular, you will see later, to preserve the asymptotic limit and also the positivity of the solution will be very important for this kind of equations. Okay, so. So here's a brief outline of my talk. So I will start by introducing the hyperbolic and kinetic equations, and then discuss the numerical challenge. So why this is difficult to get a high order time discretization. And then I will introduce mainly two methods in this talk. The first one is the so-called multi-derivative IMEX Runge-Kutta method. And the second one is the splitting. So I put a quotation mark there. So you'll see it's not really a true splitting method, but it's a splitting-like method. Which achieves actually a different properties compared to the first one. So, and then I'll conclude. All right, so let me start off by just stating our goal clearly. So throughout this talk, what we have in mind is the following model problem. So this is an ODE system where you see the solution U is an n vector. And on the right-hand side, you have two operators, which I denoted by T and Q. So, so one is Steve, the other is possibly, one is non-Steve, the T operator, and the Q is possibly Steve, as indicated by this small parameter epsilon. So in the applications that I consider, this epsilon is a parameter that could ranges from very small value to order 1 value. Okay, so I also highlight there this Q is often nonlinear in my application, and you will see this also play a important role in the later analysis. So we further assume this problem satisfies two properties. So one is a positivity property, as is clear. So when the initial condition is non-negative, the later solution is always non-negative. The other one is the asymptotic limit. So namely, for this kind of problem, when we send epsilon to 0, there exists a non-trivial asymptotic limit. I'll give some examples on next slide. So our goal is the following. So we want to design a time discretization method for this model problem such that it's high order. By high order, I mean it's at least the second order. So you will see even designing a second order method is not easy in this case. And positivity preserving, right? So to admit this positivity property of the continuous problem, and also asymptotic preserving. So which we call it AP. So basically, a numerical scheme to be AP means we want to mimic what happens at the continuous level. So basically, you want to have your numerical scheme, and then you fix your time step, delta t, and you send epsilon to 0, and you want to check what your numerical scheme becomes in this limit. So if in the limit, this scheme becomes a consistent discretization to the corresponding limiting system, then we call this scheme AP. Okay, so that's what we are looking for. And of course, we don't want the order reduction. So in preserving this asymptotic limit, we want to preserve the same order of my original scheme. So this is the general goal. And now let me give you two examples that we have in mind. The first one is a so-called hyperbolic relaxation system. So this is a hyperbolic system. As you can see, we have unknown like U1, U2, right? Two functions, depends on time t and space x. And on the right-hand side of the second equation, we have a possibly Steve relaxation term. And here, this function f could be nonlinear, okay? And to see this system has a asymptotic limit is very easy to formulate. So basically, you focus on the second equation and you send epsilon to 0. Then formulate, this will drive U2 to f of U1, okay? And then you use this information, so you substitute this into the first equation. You can close it actually to get a closed equation for U1. And this is the familiar nonlinear conservation law, right? So in other words, if you start from such hyperbolic relaxation system and send epsilon to 0, you will recover in the limit a non-trivial equation. In this case is a nonlinear conservation law. Okay, here comes another example. This is really a equation from kinetic theory. So I should say the most fundamental equation in kinetic theory is the Boltzmann equation. I don't know if I've heard about it, but here I don't want to really show the Boltzmann equation because my experience tell me that once I show that, because the equation is so complicated, I will lose my audience. So I will not do that, but I will just tell you that this full Boltzmann equation is a really complicated nonlinear integral equation. And because it's so complicated, people look for simplified model to mimic its properties. And the so-called kinetic BGK model is, so I should say, the most widely used model. So let's look at this equation. So the unknown here, F, is the probability density function. So basically, this F depends on time t, position x, and the velocity v. So it's a function lives in the phase space. Okay, so it tells you the probability of finding a particle at time t, position x, and velocity v. Okay, and then this equation essentially models two effects. One is the particle transport, and one is the particle collision. So when the particle in a system, when there's no external force or so on and so forth, this particle will travel with its own velocity. Okay, so that is indicated by this transport term on the left-hand side. And this particle will eventually, or perhaps collide, hit another particle, and then they undergo collisions. Okay, and then the right-hand side actually models this collision effect. So the true Boltzmann equation actually does that, which is the reason why it's complicated. But the BGK model seeks a simplification of that. It's essentially a collision or relaxation type operator, which tells you that F will be eventually driven to the local equilibrium, the so-called Maxwellian. So this Maxwellian is a function, as you can see, this is a Gaussian function, and depends on the density and temperature and also the bulk velocity. These are not given independently. They are the quantities defined by the moments of F. So you see this Maxwellian is a highly nonlinear function of F. So basically, you give me F, I take the moments, I obtain all these macroscopic quantities, I use them to define the Maxwellian. So the way to design the operator like this is to make sure my right-hand side conserves maximum momentum and energy. So which means when I multiply by 1v and v squared and integrate, I get 0. Okay, so that's conservation. That conservation property is very important. And in the kinetic context, this epsilon has a physical meaning. It's a so-called Nussen number. It's defined as the mean free path, the ratio of the mean free path, and the characteristic length. So essentially, this epsilon tells you how dense your system, your particle system is. So you can think of, so mean free path is the average distance traveled by a particle between two consecutive collisions. So if mean free path is very small compared to the typical length of your system, you can imagine this collision happen very frequently in your system so that the system is nearly like continuum, so can be treated like equilibrium. So in that case, in fact, you don't have to use kinetic equation. You can use the fluid equation. Okay, so that's why we call this fluid region. And on the other hand, if epsilon is order 1, we are really in the kinetic region. Okay, so talking about this model, let me quickly show you how we can get a non-trivial asymptotic limit. So basically, I start from the BGK equation. I do the moments. This is what I briefly described before. So I will introduce this phi, which are called the collision invariants, and then use the bracket to denote the integral with respect to v. So because my Maxwellian is defined in this way, okay? So if you carry out this integration, you will see the right-hand side will be identically 0. And then the left-hand side, you will get a moment system. So here I use capital U to denote the macroscopic quantities. So you have the density, momentum, and also the total energy. Why is this non-closed? Because you see the flux term relies on one order higher moments of F, which we don't know. So this is non-closed moment system, but to really close it, we can check the limit. So what happens when epsilon goes to 0? So when the system is dense enough, this implies in my BGK model, F will be driven to the Maxwellian. So then if you replace this F in the flux term by the Maxwellian, and since the Gaussian function, we can integrate its moments analytically, and in fact, it can be written equivalently in this form. For people who work on fluid dynamics, I guess you can recognize this is a compressible equations. So basically, starting from the kinetic BGK equation, and you send the Knudsen number to 0, you also recover a non-trivial asymptotic limit, which is Euler equations. Okay, so now let's talk about the numerical challenge. Going back to this model problem, and as you can see, we have apparently 2 operators. One is non-stiff, the other is possibly stiff. So a very natural way to solve this equation, as we know today, is to use the IMEX, right? Implicit-explicit Runge-Kutta method. In fact, one of the classical work is done by Will, Steve Rose, and right here. It's now has become becoming one of the standard methods people use for time discretization of the kinetic equations. So it's very natural idea. And when it's applied to our problem, I think I should make 2 remarks. So one thing to say is we have seen that the stiff term in the hyperbolic relaxation system and also the BGK model, these are really nonlinear operators, right? You may wonder if I treat this term implicitly, then you have to solve a nonlinear system, which is not desirable. But in fact, as we'll see a second, due to the spatial structure of this collision operator, we can solve this implicit scheme in an explicit manner. So without iteration, so that which is nice. And secondly, when you care about the AP property, right, to preserve the asymptotic limit at a discrete level, this is usually also not very difficult to obtain. In fact, the classical methods introduced in this paper is already AP, so for the kinetic equations. So let me show you how, just if you are not familiar with IMEX method, so I would just want to start with a very simple first order method to show you how it works for our problem. So coming back to this hyperbolic relaxation system, first order IMEX scheme is very simple. Basically, you see the left-hand side is non-stiff, so we treat it by a forward Euler method, and the right-hand side is stiff, which is done by backward Euler. Okay. Now, the first issue to answer is, can you really solve this explicitly? And the answer is yes, and it's very easy to see. Basically, you solve these 2 equations in order. You first solve the first equation to obtain U1 at n+1. Okay, and then you use that in your second equation. Since this f is nonlinear, but u1 is already known, right? So this is not the issue. You can solve a second equation for u2 very easily. So that's why I say even it's a nonlinear stiff term, it can be done explicitly. And the scheme is AP. So what I mean by this more precisely is the following. So we take our discrete scheme, but ascend epsilon to 0. Then from the second scheme, you can see that second equation, you can see that U2 n+1 will be driven to the corresponding equilibrium. So this will happen as soon as the first step, right? So, and then if you use this limit in your first equation, then you get this, right? And after first time step, okay? So this tells you that in the limit, your numerical scheme just becomes a first order in time scheme for the nonlinear conservation law. That's why it's AP, okay? And furthermore, this scheme has many good properties. So the scheme is positivity preserving, in fact, and it's also very easy to see. So here I just rearrange terms a little bit. It's the same scheme as I show up here. So now you see, if I start with non-negative U1, U2, as long as I do the transport term in a positivity preserving way, and this can be very easily achieved by imposing a standard CFL condition, right? For these 2 parts. Then for the U2 n+1, you see this is a convex combination of 2 terms, which are both non-negative because this f by its definition is a non-negative function. So you also preserve the positivity of the solution. So yes, and also I should say, you see, the only condition you need for positivity preserving is a standard CFL condition that's imposed from the transport term, not on the stiff term, which means your stability constraint delta t is independent of epsilon. And this is what we really need. So now, if we understand how it works for the relaxation system, it's very similar in the BGK case, although it's a little bit more involved, I should say. So you take this BGK model, and I do, again, a first order forward and backward order coupling, right? I got this scheme. And now you see, since Mn+1 is so nonlinear, how can you do this explicitly? The trick is, in addition of solving this equation, we also involve a moment system. So we take a moment on this scheme, okay? Namely, I just multiply the equation by phi, my collision invariance, I integrate in V. Since the right-hand side is conservative, so I get 0. So you have this non-closed moment system, which is fine. Basically, given Fn, you can first solve this moment system to get Un+1. And these are the macroscopic quantities. So which means you know rho ut at the new time step. With those, you can easily define the Maxwellian because this M is exclusively, dependent on this rho ut. So once you have Mn+1, then you use it back here to this original scheme. Since Fn+1 is linear, so you can easily solve for it. That's how it works. And the scheme is AP, very similar to the previous case. So when epsilon goes to 0, you see Fn+1 will be driven to the Maxwellian. And you use this in your moment system to replace the flux term F by M. And this is nothing but a first order kinetic scheme people use to solve the compressible equations. So the scheme is also AP. And furthermore, positivity preserving follows similarly as before. So you can write Fn+1 as a convex combination of two non-negative functions. And in fact, at this point, I should mention why positivity is important for our problem. You see the Maxwellian depends on rho u and t, right? If your F becomes negative, which means your density and temperature could become negative, so your Maxwellian is not well defined. Right, so that can be problematic in the numerical simulation. And one additional property that is also interesting to the kinetic equation is it's also endowed with the entropy structure. So basically, with this first order IMEX scheme, since it's really a convex combination of two non-negative functions, you can easily show the entropy also decays with time. So the entropy in the kinetic equation case is the Boltzmann entropy is F log F integrate with respect to V. And if we discretize in space, so this is a summation in space. Okay, so now let's see why this is. So this is how it works in the first order case, right? Then to apply the IMEX Runge-Kutta scheme to get a high order IMEX Runge-Kutta is fairly standard. We know very well by today. So basically, you can use the explicit Butcher table to solve to discretize the non-stiff term, and use the implicit Butcher table to discretize the stiff term. Okay, and here you see this J ranges from 1 to I-1 is to make sure this is really explicit discretization. And for this, it's like a Dirk method, right? So J ranges from 1 to I, but we do not allow anything beyond the diagonal. That is to ensure the computational efficiency. So this is fine, and people already considered their application to the relaxation problem and also the BGK model. And as I said, like the first order case, it's not too difficult to show the high order scheme is AP. So this is not an issue. But if you want to ask for more, so if you want to get also a positivity preserving property, this is not so clear. In fact, so we have seen that it works in the first order case, but I should tell you that once you go beyond the first order, there is an order barrier. Why is that? So let's think about the AP property. So requiring AP, basically you want your time step to be chosen independent of epsilon, right? So that you can pass a limit. But this means you have to do some implicit treatment in your scheme. On the other hand, it has been shown in 2001 that there does not exist unconditionally implicit strong stability preserving method that is higher than first order. So in case you don't know SSP, this is like a stronger property which includes the positivity as a subcase. Okay, so this is essentially tells you that even though I get rid of the explicit term, consider the implicit collation, only the implicit collation term in my equation, and I want implicit treatment, still want to preserve the positivity, I cannot go over beyond this first order. There is an intrinsic barrier there. Okay, so now the takeaway at this point is, unless we introduce something new, there's no way to get a high order positivity preserving and AP scheme within the conventional IMEX framework. But does this mean this is the end of the story, right? So now I'm going to show you two methods which can actually overcome this order barrier. And it's not a conventional IMEX scheme. We have to do something more, right, to get out of this framework to do that. So let me start with this first one. So I call it the multi-derivative IMEX Runge-Kutta. As the name implies, it relies on the derivative information of my operator. So to be precise, I'm going to use a very special property of my collation operator, which is related to its Fractal derivative. So I'll use this Q dot to denote Q prime, the Fractal derivative of Q applied to Q. Okay, and just to remind you, the definition of this functional derivative is defined as follows. Basically, at point U, okay, if you want to hit it on V, you just take the limit along the direction of V. And if we go back to these two model problems, so hyperbolic relaxation system, where in the abstract way, I will define my U to be my solution vector and T to be the transport operator on the left-hand side, and the Q to be the relaxation operator. And you can easily verify by using this definition. I'm not going to do it here, but it's a very easy calculation. If you do the Q prime X on Q, this is equivalent of just putting a negative sign to Q. This is kind of surprising, but think it a little bit further, this Q is really like a dissipative operator. So when you hit Q prime to Q, this is like equivalently of acting a negative action to my Q. So which kind of makes sense for dissipative type operator. And similarly, if you do the calculation from the BGK operator, you can get the same conclusion. Okay, it's not obvious, but just use this formula, it can be verified. All right, so now I'm going to start construction of the scheme. So let me go back to this model problem once again, right? This can be obtained from the method of lines discretization of my PDE system. And T is the transport operator and Q is my relaxation or collation operator, just to remind you. And to start off, we want to impose some conditions. Basically, I'm just recapping what I have said before. So the first condition says that if I start with a non-negative U and apply a forward Euler step to my transport operator, under a standard forward Euler CFL condition, I can preserve the positivity of the solution. And this can be done, right? As we said, as long as we choose a proper spatial discretization under a CFL condition, this can be satisfied. This is not an issue. And the second assumption says that if I apply a backward Euler discretization to my collation operator, it's also positivity preserving. And this is not so obvious, but it can be verified by the, for my two problems, model problems. And it's positivity preserving unconditionally. So for any delta T. And the third property is what we have seen on the previous slide. And the last two properties looks a little bit abstract, but trust me, they are just an abstract way of re-summarizing the properties that I already told you. So basically, this one says that my collation operator is conservative in some way. So if I apply a linear operator R on this collation operator, I get 0. And the last one just tells you that there exists an equilibrium, or there exists a kernel. To non-trivial kernel to my collation operator, which is denoted by this. And with these two properties, essentially you can ensure that this model problem has a asymptotic limit. Once again, this is just an abstract way of restating what happens for the BGK and the relaxation case. So you take your model problem, multiply by this linear operator R from left-hand side on all terms. And because the collation operator is conservative, so you get 0. And you get this non-closed moment system. On the other hand, when epsilon goes to 0, this collation operator becomes 0, then your U will be driven to the local equilibrium denoted by E of omega. This omega is a reduced variable. Okay, if you substitute this into your equation, you will get a closed system for omega. So that is your asymptotic limit. Okay. So with all those assumptions, our scheme, in fact, comes in a very straightforward way if we follow the machinery in the SSP community. Basically, we propose a S-stage multi-derivative IMEX Runge-Kutta scheme in the following so-called Shu-Osher form. So you see, it's very much like a standard IMEX Runge-Kutta method, but it's written in a special way that you can easily impose the positivity condition. So at every stage UI, you see this is Ri times UN, right? And then you have some combination, convex combination of the previous stages. And then you have a discretization of the transport term, and you have the implicit treatment of the collation term, and additional term, which involves Q dot, which I mean is a Q prime, X on Q. So this is really the new term that we introduced to break the order barrier, because without this term, it's just a conventional IMEX type scheme. And to see this better, we can write this in matrix form. Again, it's very straightforward, right? Just using a matrix notation. For those of you who are more familiar with the standard Butcher form, there is actually a correspondence. So starting from the Shu-Osher form, and you introduce the matrices A hat, A, and A dot, you can convert that Shu-Osher form to this familiar Butcher form. Okay, and in this way, I also write down its component form, so you see easily compared to what I just discussed, IMEX standard IMEX Runge-Kutta scheme, the new term is a right term, shown here, which involves the derivative information. Or you can see this is like using a derivative as a correction to break this order barrier. Okay, so now we have an ansatz of the scheme, and we need to find all these coefficients, right? We have to be able to find the coefficients, otherwise this is not a valid scheme. And now we need to impose various conditions. And the first thing, of course, we need the method to satisfy the order conditions, which means in the non-stiff region, when epsilon is order 1, we satisfy first, the second, and third order conditions. Okay, and this is just some formulas. And then we need the positivity preserving condition. As I said, written the method in the Shu-Osher form allows us easily to identify the condition to ensure the positivity. Basically, you just need all these matrices up to D to be non-negative to ensure the positivity. And for the very last term, I actually require this D dot to be non-positive. Why is that? Recall again, Q dot is essentially equal to negative Q, right? So you have a negative sign there. So to get the positivity, you have to flip the sign of D dot. And once you satisfy all these conditions, it's very easy to see you preserve the positivity. Okay, and finally, the condition for AP. So how can you get asymptotic preserving property? This involves a little bit more calculation, but intuitively, what you need is at every stage of your Runge-Kutta scheme, you want, when epsilon goes to 0, you want your scheme to drive your solution F to the corresponding equilibrium. With that being said, you need these collation terms to play a role. You cannot let them vanish. So basically, all we need is to require either of these or both of them to present at every stage. So it's a very simple requirement. And with all these conditions, combining all these conditions, we are able to find the second order method. The matrix, yeah, the formula doesn't matter, but maybe I just want to mention, you see the D and D dot, they do not vanish simultaneously. So this is very important to ensure the AP property. And also we obtain a very good CFL number. So the CFL number is 1 in this case. And also we are able to find the third order method. Once again, these are the formulas for D and D dot, and the CFL number is close to 1, almost optimal. Okay, so let me quickly show you some result to convince you how this works. So I'll do an accuracy test on an ODE model. So essentially here, f is a nonlinear function, g is also nonlinear, and we choose the initial data such that it's inconsistent. What I mean is we do not start from equilibrium, okay? And here's the results of the second order method and third order method. And how to read this, so you can follow my cursor. So basically we change the value of epsilon from order 1 to 10 to the minus 10. So from non-stiff regime to very stiff regime. So when epsilon is equal to 1, this is a blue line here, you see a perfect second order. And similarly here, you see a perfect third order. We don't care about what happens at very small delta t, where you may have a round of error. And as you decrease epsilon, and you see this right curve, we lose the accuracy, right? We gradually lose the accuracy, and this yellow one, we no longer see the desired order. But interestingly, you see when this epsilon decreases further until it becomes very, very small. So for example, if you check the blue one and also the green one, the light blue one, and you see we recover the original order of the scheme. This is exactly due to the AP property. So because our scheme is AP, so in the limit, your order reduction is gone. So it's going back to the design order of your scheme. And you will see the same trend in the third order method as well. Okay, so another quick test just to convince you why, so the positivity preserving property and also the AP property. So we consider this 1 dB GK equation, where we choose this epsilon to be a time, spatially varying function to really make this like a multiscale problem. So within the domain, this epsilon, we design it in such a way that part of the domain epsilon is order 1, so in the kinetic regime, and in part of the domain epsilon is very small, so you are in the fluid regime. So choose the inconsistent initial data. And since here we also consider, so we consider PDE, we need to use a proper positivity preserving spatial discretization to make the overall method positivity preserving. So we choose the fifth order finite volume Binot scheme with a positivity preserving limiter to make sure that. And here are the results. So basically, you see this is density, velocity, and temperature. And the reference solution, the black lines here are the ones that are obtained by a fully resolved explicit SSP Runge-Kutta scheme. And the red dot, the blue dots and red circle indicates the result by our second and third order method. So you see it actually match very well. And in particular, I want to mention because the method is AP, so our method can use a much larger time step to get this calculation. Okay, so I have 10 minutes. So now we have a nice IMEX method which overcome the order barrier. You may wonder, why I want to consider a new method. Okay, so as I said, it's a second order and also third order, both positivity preserving and AP. But you may also notice that this scheme highly relies on a special derivative property of my collation operator. Namely, I have to make my Q to satisfy this condition in order to really apply the scheme, right? Otherwise, I don't know how to evaluate this fracture derivative, right, for a complicated operator. So this makes this method a little bit restrictive, because especially in kinetic theory, there are many equations which whose collation operator, in fact, does not satisfy this property. For example, the Full-Boltzmann collation operator, which I refrained to show you the formula. It's a nonlinear integral operator, although it also has a dissipative structure, but it does not satisfy this property. And there are also like a diffusive type operator, for example, the Fokker-Planck operator, which also does not satisfy the property. So the question is, can we have a method that can treat more general operators? Now let's think out of this IMEX Runge-Kutta framework and think about something different. So if you come from the splitting community, you may wonder, why don't you try splitting for this kind of equation? So in fact, we can, and it's actually also widely used in our community, because there's a reason. Okay, so you have this kinetic equation, and if we do a first order, say Lee-Trotter splitting to split the transport term and transport step and also the collation step, does this does this have any advantage? And the answer is yes. So once you split these two steps, in fact, the collation step is often easier to solve. What I mean by that, although I'm now aiming for more general kinetic equations, but I still want to use the BGK equation to illustrate the case. So think about the BGK equation. So if I take out the transport term and only consider this relaxation or collation term, and I can still take the moments like I did before many times, then the right-hand side is conservative, so I get 0. The left-hand side is nothing but the time derivative on the macroscopic quantities, density, momentum, and energy. This essentially tells you the moments doesn't change with time once you take out the transport. Then you see if this M doesn't depend on time, this essentially becomes an ODE, which can be very easily solved. In fact, it can be solved exactly, right? So your solution F at time t will be a convex combination of your initial condition F and also your initial Maxwellian. So and although I don't want to show the other cases, but for the other equations, there are also similar properties. Okay, so we consider first order splitting, and we now want to get a higher order method. Then you may ask, okay, why don't you try the strong splitting? Right, that's a very natural step. So let's see if this method is going to be successful. So if we do the strong splitting, for example, we do a half-time step transport and one-time step collation and another half step of transport. Will this and then say we use a positivity preserving time discretization for each substep. Would this serve the purpose? The answer is, if you consider the AP property, this is not a good scheme, in the sense that you will suffer from the order reduction in the limit. Why is that? It's very easy to see. So when epsilon goes to 0, essentially your collation step drops out. This just becomes a projection. The effect of this collation step is just to project F to the local equilibrium immediately. And then cross out this middle step, what you are left with are just like a sequence of forward Euler time stepping of your transport steps. So that's why the method, in fact, becomes the first order scheme in the limit. So the simple strong splitting will not work. But since we know the splitting is nice, right? So we can take advantage really of this simple structure of this collation equation. Let's think about something that is of splitting nature, but maybe not quite splitting. So that actually leads us to the following scheme. And I call it exponential Runge-Kutta because we need to use the following notation. So basically, once again, this is my model problem, and I will denote the solution. So take out the transport term and consider only the collation term. I will denote the solution map to this collation step by a function phi s. Okay, so my notation here means I start from the initial condition u of t0. I advance this equation to t0 plus s. Then the solution at that time is denoted by this. So using this notation, this solution map, our proposed scheme, or I should say the ansatz, looks like follows. Basically, let's see this step by step. So we first do a fractional step of collation, and then we do another fractional step of transport. We do another sub-step of collation and another step of transport. So up to this point, it's just like splitting. But you see, it's the very last step which makes this a non-splitting scheme. It's really not a splitting because you see, this is like, so we want to do some kind of convex combination of U2 and also this UN, this term never appears before. In fact, this you have to compute this part. And then finally do another collation step. So why we propose this ansatz is really driven by the AP property. We want to make sure we put this collation solver or map into the proper stage so that we can drive my solution to the corresponding equilibrium. And here, all these constants at this stage need to be determined. Okay, so for this scheme, I can do the same thing as before. I want to impose various conditions, right, to make sure it fulfills my requirement. The first one is the order condition. Unfortunately, by this ansatz, we can only do up to second order. So we impose a first and second order condition. And we also impose a positivity preserving condition. And once again, using this ansatz is very easy to impose a positivity condition. Basically, you just need to make sure all these constants to be non-negative, right? And also, so A2 and W, because they also appear as 1 minus W and 1 minus A2. So you want them to be bounded above from 1 and under the CFL condition. And this is due to your 2 transport steps. And finally, the AP conditions, as I said, the consideration here is really to make sure I have inserted all these proper collation steps in my scheme so that it will be drive the solution, the intermediate stage solution to the corresponding equilibrium. Okay, now with all these conditions, if we maximize the CFL number, in the end, we get the following scheme. So it turns out that you have 1 degree of freedom, which is denoted by A0. So as long as you choose A0 between 0 and 1/2, this will be fine. All the conditions will be satisfied. And the CFL condition, in fact, is the forward order CFL condition. And to see it better, maybe you just, so look at this. So when spring goes to 0, or you forget about all these phi terms, just look at the transport term. What is this? This is nothing but explicit second order Helm's method applied for the limit system. So which means in the limit, you don't have order reduction, you still maintain a second order. And one more remark. So to design this scheme, of course, I rely on this exact flow map of my spatially or the collation equation, but this is not necessary. This can be relaxed, right? Because overall we are content with the second order method. So you can replace this by approximate solver as long as the solver is second order accurate and does not break the positivity preserving and AP property, then you are fine. In fact, this freedom allowed us to treat a more general class of relational kinetic equations, which I will not bother you with the details, but we can do BGK and we can do a more generalized BGK, even full Boltzmann and Fokker-Bloch equations. So it's nicer, but of course the downside is we can only do it up to second order. Okay, so I think with that, I'll conclude. So basically, we introduced two time discretization methods for the stiff, hyperbolic, and kinetic equations. So which are both positivity preserving and also asymptotic preserving. The first one relies on a derivative correction term, which can reach third order, and the second one is only second order, but it works for more general correlation operators. So I should say, emphasize once again, by requiring the method to be AP, your time step constraint, in fact, only comes from the non-stiff term. So it's independent of each one, which is very important. And finally, although I never mentioned this in my talk, we only concentrated on the positivity preserving property, but in fact, the methods I introduced are SSP. So because you see, they all rely on convex combination of various terms. So the scheme is more general in the sense that they will preserve any convex functional bound that is satisfied under the forward Euler scheme. So that means the entropy decay is a direct consequence. So with that, I thank you for your attention. Okay, yeah, I'll put some references there, just in case you're interested.
Fantastic. Questions from the audience? Don't ask me any questions about the bank. Thomas.
I'm not sure if I can formulate it correctly, but I try. In the kinetic model, you have the velocity variable, conditional variables. You have space and velocity for kind of R of 2n. And discretizing in velocity space is always a problem. But I didn't see this in your scheme.
You're right. When I talk about this, I assume the velocity space is treated well, namely the velocity discretization does not break all these properties. So in practice, this can be done I should say, it's not in a strict way, but it can be done near optimal way. Basically, your function for kinetic equations, the solution always decay very fast. In the velocity space. So you can always choose a large enough computational domain in V, and then do a nice discretization in the velocity space too. But you are right. In fact, in principle, what I presented here is assume the velocity space can be done perfectly so that it will not enter or introduce any error to here.
Can you go back to the slide where you showed strands?
This one, right?
That's good. So one of the things people even say a lot is that when you go to, so this is second order splitting.
Right.
If you want to go to third order splitting,
Mm-hmm.
you have to take some backward time step.
Yes.
So does that concern you at all?
I think that would be an issue, especially maybe for the transporter, not so much. Nowadays, we can do downwind, some kind of downwinding, right? But you see this collision, if each one is order one, probably is fine. But if each one is very small, because this is really a dissipative equation, which has an entropy decay structure. If you solve this backwardly, there may be issue there, I think. Yeah.
Anyone else? Okay, well, let's thank you again.
Thank you.
I guess it's back.
Yes.
So I can see all. So well done. Very good job. So honestly, what you said about the integrating that Q backwards in time is locally unstable, but I think we can put it together so that at the end of the step we should get stability.
If you just solve it over a dirty t-cap step, perhaps it's fine.
Yes, but it will be a sub-step, and so
Yes,
you will
yes.
be somehow counteracting.
Yes,
you know,
yes.
violations.
But you may still have this order reduction, right?
That I don't, well, yeah, I don't know. I don't know. Maybe yes, maybe no, right?
Mhm,
So I think it would be,
The thing is, either at least the way I think about this is, essentially you just take out all the collation steps in your scheme. It becomes just like a discretization on the transport term.
Yep.
And that depends if you still have a second order. Oh, sorry. If that still maintain the original order of your splitting scheme. If it does, then it's fine.
Yeah.
I guess probably, yeah, I don't know.
Yeah. Well, I think it would be interesting to try it out because I suspect that, because otherwise you're kind of at a ferry, right? If you,
Yes, that's
right, you
why,
can't go past
that's
second
what,
order.
yeah. In fact, with Go, we look, I mean, we look very hard
Yeah,
into
yeah.
this problem. We try to see if we can get a third order
Yeah.
method. I'm not entirely sure, but I think I'm keen to say that there's an order variant from there to get from second order to third order.
I think we can do it.
Okay,
Okay,
that would be
so-
great.
I think we can do it, but to convince you, I want to use your system. So what do you, these examples you have, or what are they coded in what language?
MATLAB, we
MATLAB?
do a very simple
Okay.
test.
So maybe I'll send you an email and you can send me your system.
Sure. In fact, I think one can even just start from this ODE example,
Yep,
which is also nice. It's just like wonderful
Yeah, exactly.
system, but it's discretizing a bit different way to really mimic the structure of this hyperbolic relaxation.
Did you meet
system.
my student Vicky? She was here. She's,
Yeah,
There she is,
yeah,
actually, just by
she
the
gave a
door.
great talk
yeah.
yesterday.
So,
Yeah, I didn't have a time to talk to
no,
her.
that's okay. I was
Yeah.
gonna say, I will task her with this problem.
Okay,
Right, 'cause we
sounds
have
good.
software
I'll
that
be
is-
very.
Yeah, we
Yeah.
have software which is kind of general, like you can
Oh,
put
maybe
in
we
whatever
should
part you want. We should stop the sharing and stop the recording.
Glad I finished on time, so I don't prevent people going to banquet.